The following video is an introduction into imaginary numbers and then complex numbers. So first of all, what are they? Well, I'm just going to write down some equations here and just see if you can solve these. So which of those can you solve? Well, I guess a lot of that depends on your mathematical knowledge, but it also might depend on the moment in time. So for example, the first one there, if you lived in a time before mathematicians had discovered rational numbers, then you wouldn't have been able to find a solution to that. For the second one, there was a time when we didn't really have a concept of zero. So if you lived in that time, you wouldn't have been able to find a solution to this equation number 2. And what about the third one? A long time ago, there was no concept of negative numbers. So solving an equation like that would have been impossible. And the fourth one, well, the square root, and there's positive and negative of course for that, of 3 cannot be written as a fraction. It's not an irrational number, and for a long time we didn't know that these numbers existed. So depending where you were in time or when you were trying these questions, you may or may not have been able to solve them. But now, with the mathematical knowledge that we've got, we can solve all of those. But what about the last one? Do you know how to find the solution to x squared is equal to minus 1? Well, you might do if you've heard of a special number called I. Now, I is a number such that if you square it, you get minus 1. And I'll come back in a minute to why we have that number and how it's been developed. So if the square root of minus 1 gives us a solution to this, then in fact we have 2 plus or minus I for that. So this is this strange new number, I. Now, because I is dealing with square roots, it might lead you to believe that it developed from solving quadratic equations. And in fact, up until now, you've not been able to solve equations like this one here. So if you use the quadratic formula for that, we have a problem here that b squared minus 4ac gives us a negative number. (25) subtract 28 is negative 3. And because we've not been able to solve this up until now, we've said that that's got no real roots, and we've stopped there. So the development of the number system has allowed us to find a solution to this. In mathematics, we've been able to solve this sort of equations, the quadratic equations, for thousands of years. The ancient Babylonians, although they didn't use algebra like this, were able to solve this type of equation. So this is not a new thing, it's not a difficult concept at all. However, when we got to an equation like this, we just said it was impossible, and we stopped there. And the development of the number system didn't actually come from quadratics at all. It came in the next step with some work in the 16th century on trying to solve cubic equations. So here's a cubic equation. We've got x cubed is equal to 15x plus 4. Now just pause the video and just see if you can find a simple number solution to that. You should have been able to see that x equals 4 is a root of that equation. 4 cubed is 64, and 15 multiplied by 4 add 4 is 64 as well. So there's a very simple root to that equation. Now, not all cubic equations are as simple to solve as that one, and the formula, if you look for it, and you could find it, is really quite complicated. compared to the quadratic formula. And in the 16th century some mathematicians worked on this and found solutions to more and more types of these cubic equations. So depending how you rearrange it made the equation easier or not to solve. And there was a mathematician called Tartaglia who found a nice way of being able to solve more and more types of equations. And at the time, if you were a mathematician and you wanted to make a living, what you had to do was kind of publish mathematical journals. But to be able to do that, you had to have some financial backing. Now Tartaglia at the time didn't have this, and so what he did was he kind of had entered himself into mathematical competitions. So I guess at the time it was a bit like the X Factor for mathematics, and what two mathematicians would do would go head to head and challenge themselves with problems, and you can imagine a crowd watching them and perhaps even betting on the outcome of that. So one time Tartaglia found a way of solving a new type of cubic equation that other mathematicians at the time couldn't solve. And one of the mathematicians who he beat in one of these competitions and made himself some money and a little bit of fame was Cardano. Now Cardano was quite keen to sort of find out the secret that Tartaglia had found, but obviously Tartaglia wanted to keep that to himself and he wanted to publish his work. Anyway, to keep a story short, Cardano did eventually get out of Tartaglia the method for doing this, and he actually told him how to do it in the form of a poem which Cardano used. Now Cardano shared this information apparently with one of his students, and one of his students found out something quite interesting about this Ferrari. He used it, and in fact he was able to or Tartaglia sort of challenged him to another mathematical duel, and actually lost this one because Ferrari got better at solving the equations than Tartaglia did in the first place. However, Ferrari noticed something about solving certain types of equations that was quite strange, and he noticed that some of them were just impossible to work out. So they had this formula, it was in the form of a poem, but sometimes it just didn't work out, and he kind of discussed this with other mathematicians at the time. Another mathematician worked on this and found something really quite interesting, and that whilst it didn't work and it gave us something impossible, that if you just ignored the fact that it was an impossible number that came out of this formula and just worked it through as you would do with an ordinary number, then a solution came out. And that's the case with the equation that I've just showed you there. So let's just run through this for a second. So what we're trying to do is solve equations like the one that you just did previously. Now the formula was a bit complicated, but what you end up with in the end is something a little bit like this. So to find the value of x to solve the equation, you've got to do some sort of cube roots and some square roots, but for the equation that we've got there, you ended up having to square root a negative number. So the mathematicians at the time said, well, that's just impossible, we can't solve that type. But Bombelli said, well, just carry it on, work it through and see what happens. And he found that actually if you did solve it, then you'd get the solution that we'd found just now. So if we take these two separate parts here and we call them a plus bi, so bi, the I now we know is this imaginary number which is the square root of -1, which obviously they wouldn't have used that notation at the time. So if we can imagine that those two parts are what we get, then when we put that back together something strange happens, that those two parts with the I just cancel out and you get 2a, which is the solution that we found before, since a is 2, of x being equal to 4. So that, I remind you, is what you found to the for the solution of this equation before. So it just seemed that if you ignored the fact that this thing here is just an impossible calculation, you can't find the square root of a negative number, and just worked it through and did your calculations as usual, then it worked out. So the mathematicians at the time said, well, if it works out and we can do calculations with it, then shouldn't we be using this number? And that led to the development of imaginary numbers. Now it's worth noting here that it took time. So mathematicians debated for years and years about whether we should allow these numbers to be used. I think it was Newton who called them impossible. Other mathematicians said they were imaginary, and you can see why. They just don't seem to be in the real world. They're in our imagination. But imaginary numbers are actually extremely useful, and we use them a lot in electronics. So they allow us to make really complicated calculations much simpler by using complex numbers, imaginary numbers or complex numbers, to solve equations that would take us a lot of time. So it's said that a lot of the invention or the television that you probably watch at home works a lot better now because of the calculations that we're able to do with complex numbers that would have been a lot longer and more time consuming to do without. But you know, it's one of those topics that yes, there is a use to it, but the thing that I enjoy most about complex numbers is the beauty and the geometry behind them, and that's what we're going to look at, and I'm sure that you'll enjoy them because of that. So let's just do a bit of technical work first of all, and go through some examples and using those. So it allows us to solve equations like this. So if x squared is equal to -1, we've now got a solution to that. There are two roots. We get I and we get negative I. Why do we get this second one as well? Well, obviously I squared is equal to -1. That's our definition of what I is. But if negative I multiplied by negative I will give us positive I squared, then that will give us the same answer, won't it? So there's two roots to that equation. Well, what about this one? If x squared is equal to -9, well, that means we've got -1. That means that if we're trying to find x, we've got the positive and the negative square root of -9. Now 9 is a square number, so we could rewrite that as the square root of -1 multiplied by the square root of 9, and we know that square root of 9 is 3, so we've got plus or minus 3, and then our root -1 is our I. So we've got two roots to this equation. Our solution is x is equal to positive or negative 3i. Okay, let's try another one. Here's a cubic. Now I'm not going to ask you to use that complicated looking formula, but you'll notice that this can be factorized as a common factor of x there. So we could get the root x is equal to 0 and x squared is equal to -2, which means that x is equal to 0, but x could also be equal to plus or minus the square root of 2 lots of I. Okay, what about this one? So try and solve this quadratic equation, and pause the video and I'll put the answer on in a second. Welcome back. So there you might have got the answer, 4 plus or minus 6i all over 2 by using the quadratic formula. And straight away there I'm sort of wanting to do some manipulations with that, and I'm making some assumptions about the calculations that I can do with real numbers I can do with imaginary numbers as well. I've divided these coefficients through by 2, and that's absolutely fine. So there's two possible roots to that, 2 plus 3i and 2 minus 3i. So a quick explanation of imaginary and complex numbers. So the number that we've got here is what we call an imaginary number. I is an imaginary number. Root 2i is an imaginary number. 3i is an imaginary number. The number that we've got here is what we call a complex number, because it's made up of an imaginary part and a real part as well. So when we've got a real and imaginary part together, we call that a complex number. Now then, just as a side issue, if you'd have tried to solve this equation with your calculator, then your calculator might have found the solution to it. So if you turn your calculator on and just check the mode for that, there is a mode by default that will give you just real solutions. So if you try and use an application to solve that quadratic, it will just say that there's no real roots to that. However, if you just click onto this one here, a plus ib, that will find the complex roots of equations as well. So I invite you to solve that equation again using your calculator, and hopefully what you should find is the same roots that we found here. Now then, the complex numbers also allow us to do some algebra that we couldn't do in the past. So if I asked you previously to factorize this expression here, hopefully you would have no problems with that, and you'd notice that it's a difference of 2 squares, and you would have had that in the factorized form there. However, if I said to you, could you factorize this, you might struggle with that a little bit. So just pause the video and just try to imagine factorizing that for yourself now, and just see if you can do it. Could you do it? No. There's the problem, isn't there? This negative is really quite useful here in the difference of squares, because it cancels out the x terms. But there's not a way of doing it when you've got plus a squared there, unless we use I. Let's just see how that would work. Okay, so just imagine we're going to expand the brackets there. That gives us the x squared. That gives us x times by ai. That gives us x times by negative ai. So those two parts cancel out. And then at the end we've got negative ai times by positive ai. So let's just write down what we've got there. We had x squared. Yeah, let's put the two terms in that cancelled. aix minus aix, and then at the end, if we put these, we've got negative a squared I squared. Now then, that's the really useful thing, isn't it? That the I squared there is going to give us the negative of 1, so that makes this positive a squared. So we've got x squared, those two cancel out, and we've got x squared a squared. Okay, so this value I now enables it to factorize some expressions that actually we couldn't factorize before. Right, so the next thing we're going to look at is some arithmetic to do with complex numbers, or this imaginary number I. So we're going to raise the power of I to different numbers. So I to the power of 1 is just I, of course. Nothing so exciting about that. I squared is our definition of it in the first place, is negative 1. But what about I cubed? Well, I cubed is just I times I times I, or if you like, I times by I squared. Now as I squared is negative 1, then we've got I times by negative 1, in other words negative I. What about the fourth power? Well, I to the 4 is I times I times I times I, or if you like, well, what's the quickest way of doing that? That's I cubed times by I, and I've just worked out that I cubed is negative I, so that's negative I times by I, which is the negative of I squared, but I squared is negative 1, so that's positive 1. Okay, so just a quick summary of that then. So we've got I to the power of 1 is I squared is negative 1, I cubed is negative I, then I to the power of 4 is positive 1. What I'd like you to do now is just carry that on. Work out I to the 5, I to the 6, I to the 7, etc. and see what you notice. Pause the video, do it yourself. Okay, back again. So what you should have found is that I to the 5 is I to the 6 is minus 1, I to the 7 is minus I, and I to the 8 is 1. And what you should realise is that if we go for higher and higher powers of I, then that's just going to keep looping round in between these four numbers here, I, minus 1, minus I, and 1. So that's raising I to different powers. Here I've got two complex numbers. Quite often we use the letter Z to represent a complex number. If you've got two complex numbers, then you need a different letter to represent the second one, so I'm using W here. And what I want to do is just some simple arithmetic with these, just to see how well it works out. So for example, if I wanted to add these two complex numbers together, what would happen? I've got 3 plus 2i, and then I add 4 minus I. Well, it's just very straightforward. All you do is you add the real parts together, and then you add the imaginary parts together. So 7 plus I. What about if we subtract them? So it's 3 plus 2i, and then I subtract 4 minus I, and again it's the same thing. You deal with the real parts and the imaginary parts separately. So 3 subtract 4, 2i subtract negative I is 3i. And then what about multiplication? What if I multiply those two together? Well, I'm going to tell you at this stage that the distributive law for complex numbers holds, so we just multiply them out in the same way. So we can just multiply out those numbers there, those brackets, and give us the answer. So we get 12 minus 3i plus 8i, and then 2i times by negative I is negative 2i squared. Now because we've got I squared there, we can do something with that, because we know that I squared is negative 1. So I've got negative 2 times negative 1 makes plus 2 there. So I end up with 14 plus 5i. So recap, we can find powers of imaginary numbers. We'll look at finding powers of complex numbers and how that looks later on. We can add complex numbers together, we can subtract them, and we can multiply them, and then that's very straightforward. Right, I just want to go back to the number line. So this is our real number line, and we can represent all the numbers that we've had or we've come across so far in this number line. So 0, 1, 2, I can put the square root of 3, would be somewhere around there. I could put fractions on it, so I could put a third there. I could put negative numbers, of course, on this side of the line. Any number that's in the real number list we can fit on there at all. So the question is, where do these imaginary numbers go? Where does I fit on this scale? Well, that's quite an interesting question, and actually to see if you can find a solution to that yourself. So pause the video, have a think about it, and come back in a minute and see if you can find a solution. Okay, welcome back. So did you find a possible way of getting around it? Well, some mathematicians did, and when I've posed this question to students in the past, usually they find the same solution, which is great, in that if the real numbers fit on a horizontal line like this, then why can't we put the imaginary numbers up a vertical axis like this? So that I would go there, 2i, 3i, 4i, and then why not negative 1i, negative 2i coming down this way. So we have a number line, the horizontal one is for real numbers, and then we could have a vertical one like that for imaginary numbers. And what's brilliant about that is those numbers that were complex, in other words that had a real and imaginary parts, just fit somewhere in that plane. So the number minus 2 plus I would be there, minus 2 plus I. And we can fit therefore all numbers that we want, all complex numbers, in this plane. Now we tend to call this diagram where we represent those complex numbers an Argand diagram, and that's just named after one of the mathematicians who developed the idea of representing the complex numbers in this plane in the first place. But what I would like you to do here is just see how interesting the representation of this is, and how the powers of these complex numbers relates to the geometry of them. I'll explain what I mean. So imagine that we've got a complex number here, z is equal to 1 plus I. Now in the Argand diagram that's going to fit there. Now what I would like you to do is work out z squared. So z squared is going to be 1 plus I squared. So multiply that out and work out what you get. So remembering that I squared is minus 1, so we end up with just 2i. So on the Argand diagram, z squared is going to be there. Okay. Now what I'd like you to do is work out z cubed, z to the 4, z to the 5, and just represent all of those complex numbers on this Argand diagram here, and just see what you get. Okay, so that's the end of the lesson for now. That's our first introduction of imaginary and complex numbers.